Okay, welcome back, everyone. We're going to be talking today about concurrency in JavaScript. So without any further ado, let's get it going again. Where is the start presentation? There it is. Oops, I just need to grab my laser pointer yet again. Yay! This is a smaller one. Hang on. I think that's the pen. There we go. Okay, let's do this. Concurrency in JavaScript. So last time, we talked about the client-server model, and we gave a definition for what Ajax is. This time, we'll be talking about concurrency, and then we'll be talking about concurrency specifically in JavaScript. So just a reminder that what we're trying to achieve is a nice asynchronous way to have our client talk to many different servers over the lifetime of our web app, and hopefully we can devise a system so that these servers they're not only preoccupied with us, but with everyone. So Ajax gives us the framework, right? We know we need some asynchronous stuff for lazy loading, but how do we do this specifically in JavaScript? In fact, what does asynchronous actually even mean? That's what we're going to explore first. And then we're going to see how this works in JavaScript. So this will be a very brief primer for concurrency because concurrency is a big, big topic. But hopefully we'll be able to convey enough information that you guys will at least have an intuitive understanding of how all of this stuff works. So before talking about asynchronous, we probably should contrast it with what synchronous programming is. Synchronous programming is what you guys probably did in 1511 or whatever the postgrad equivalent of that is, where you write a program top down, right? You start at the top, you go down. We're guaranteed, so that's, asynchronous programs also have this idea of like top down, but what's most significant about synchronous programming is that we're guaranteed that every previous instruction will fully complete and evaluate before the next one is executed. And that gives us some very nice properties. The main one, of course, being that it's very easy to reason about synchronous programming because it's like maths in that things are transitive. If I have int a equals b and then b plus 1, and then int c equals b, then I know that c will be a plus 1, right? And it won't be a. It won't be some other random number because something has happened in the meanwhile. We know that if I store b into a, increment b, and then store that into c, that c will get a plus 1 or b plus 1 because a and b are the same thing before the increment. Asynchronous programming, on the other hand, has a few interesting things. The first one is that there are multiple flows of control. A flow of control is like an execution, right? Like you guys know what a flow of control is because if you have a regular program and then you write an if condition, you know that you can branch to two possible flows of control. Well, in an asynchronous program, it's possible that you might take both branches at the same time, depending on the state of each of those things that we call threads. A thread is a flow of control. That's sort of what the name means. And you can think of it like a string. That's kind of where the word thread comes from, because it's like it's stringing through the program. Threads, there's like different flavors of threads. They can either interleave, so that will be where one happens at one time and then the next one happens, and then it goes like this. Or you can have them literally work at the same time, and this is the hardest one. And naturally, if you think about it, that's much harder to reason about, right? Because now we don't have this nice transitivity property. Now, things could happen, things could change from underneath our feet, and we would have no idea. But let's see this in diagrammatic form. So the synchronous side, let's say we have two threads or processes or, I don't know, things. In the synchronous world, process A happens, it calls a function that starts process B's work. Process A waits while process B does its thing. And then when process B returns, process A gets the return result, the value. And then process A continues. So it's very nice, right? And this is like, if you guys remember function call, like the block diagram for what a function call looks like, it's exactly this. We're in process A, we jump to process B's function, execute the body, jump back, and then keep going. In an asynchronous world, however, we're in process A first. We then ask for process B to start doing its thing, and then process A just keep going. And then at some point in the future, when process B is done, we get back whatever information process B generated. And there's multiple strategies for knowing how to do this, how to get the response back. But this is the general idea of what's happening here. Yeah, I think I've covered most of these points. All right, so you can see already asynchronous stuff, we can get more done with asynchronous work, but it's a lot harder to orchestrate. And that leads us to like, this is more jargon, right? But there's kind of like two primary models of concurrency. The first model is preemptive. And I'm not going to talk about preemptive too much because that's out of the scope of this course. The other one is cooperative. And again, best explained through a diagram. Preemptive is this, where we have two processes literally working at the same time, same moment, and they're on different CPUs, and they're sharing information through some protocol, some strategy. And this is generally what happens when you're working on your operating system, or you're working in C, or you're working in a lower level language. Cooperative mode, on the other hand, is where it's this interleaving thing, right? Where process A executes for some amount of time, and then it stops, and then process B has its turn, and then it stops, and then process A keeps going. This is a simplified diagram, obviously. There are more nuances to this, but for our purposes, this is basically the mental model that we're working with here. So preemptive multitasking is really good for when you're doing lots of computation, obviously, because you're running two CPUs. So while one CPU is crunching numbers, the other one can, I don't know, crunch other numbers. But cooperative mode is really good for what's known as like this IO intensive workload, right? IO intensive because, I mean, this is something I'm not sure that gets talked about enough in CSE, but CPUs are really, really fast, like really fast. They're so fast, in fact, that one CPU cycle is about 1,000 times faster than reading from RAM. So you can imagine, right? If reading from RAM is 1,000 times slower than working on the CPU, reading from disk is like 1,000,000 times slower, or 100,000 times slower. How many microseconds are there in a millisecond? 1,000, right? Somewhere it's many orders of magnitude more than reading on the CPU. So if you're doing a lot of IO, you're reading from disk, reading over a network, something like this, then most of the time the CPU is just waiting, spinning. And so we're wasting time. And this is exactly the kind of work that we do when we're in the web, right? We're waiting for a user to do a thing. And humans can only like operate in the like time range of seconds. Like it takes about a second for us to click a mouse button or something like this, right? In that time, the CPU is done like 1 billion cycles. So it's just waiting and doing nothing. Or we're waiting for some information to come over the network. In that case, the CPU is still just waiting. But this is perfect, right? Because what it means is that if we just take all of the different tasks the CPU has to do for all the different things that it's trying to do at once, then we can, whilst we're waiting for, say, process A to go grab its thing, then process B can do its thing, and then process C can do its thing, and then process D can do its thing. And instead of waiting for IO to come in and then doing the next thing, and then waiting again and waiting for the next, and this sort of always waiting for IO to come in, whilst we're waiting for IO, we can go and run the other processes. And this is cooperative multitasking in a nutshell. And so we also get some other benefits with cooperative multitasking. One is that each of these processes operates like it's synchronous. So what that means is that there's no, one of the problems that happens with this kind of thing, you can imagine, right, is that if process A and process B are both isolated, as in they don't share any memory, then everything's all good. They just work on their own memory. But the world is much more complex than just isolation. So generally, process B and process A will work at some point on the same data. And that creates what's known as a data race, because whoever gets there first will change it, and then whoever gets there second will change it and confuse the first person who got there. So we don't want that to happen. And that's a data race. And data races, whenever you hear people talk about like concurrency bugs and why it's so difficult to do concurrency, data races are probably the primary reason, and deadlocks, which again, not important here. But if you think about cooperative mode, because process A runs and then hypothetically waits here while it's waiting for IO, when process B is running, process A isn't running. So even if they're sharing memory, process B exclusively when it's running will see the memory, and process A when it's running will also exclusively see the memory. So we just avoid a whole class of like problems that can potentially happen. So this is good because we get the reasonability of synchronous programming because things won't just change, but we also get the benefit of asynchronous programming because now we can do many, many things at once. They're just interleaved, right? And this is exactly, cooperative mode is exactly what JavaScript does. So for every event that needs to happen, that's known, or for every task that needs to happen, that's known as an event. And then JavaScript maintains a thing known as an event loop. And every event that needs to happen gets put onto this event loop. And then we register event handlers to go and handle that event. And each event handler runs completely isolated from every other event handler. And that's awesome. So I think that's all I wanted to say about these concurrency models. We're about to dive into the JavaScript event loop and how it happens. But let me just pause to think if there's anything more I need to say about this that's important. There is not. I will say that cooperative multitasking isn't a silver bullet. Naturally, it's really good for IO intensive workloads, but if your workload isn't IO intensive, then you shouldn't use it. I suppose that's the last thing to say. But now we're going to talk about JavaScript's event loop. And the JavaScript event loop, in essence, looks like this. So we have our event emitters, and our event emitters can be network, could be a keyboard event like you're typing something, could be a mouse event like you're clicking, or you're like scrolling, or you're just moving the mouse cursor around. All of these generate events. And for every event that gets generated, it gets pushed onto this first in, first out event queue, right? So let's say the mouse event comes first, it's event 1, and then we have some network requests that just came in, or network response that just came in, it's going to be event 2, and then we click, or type in something. I should say we press a key, not click a key. Then that can be event 3. And the JavaScript runtime, it has a loop that's running, always running. And what it does is it will grab the most, or I guess it would be what, not the most recent, the least recent event. So whichever one is at the head of the queue. And then it will check to see if it has an event handler for that. And it will go and execute that event handler, right? To completion is the main thing. It will, like I said, these event handlers always run in isolation and to completion. There's no stopping it once it starts. There's no preemption, that's called. So the event handler will go until it's done or until it decides it wants to stop, which we'll see in the last of these lectures what that actually means. But for the time being, you can think in your mind that these event handlers always work until completion. And the event loop, basically, it just always spins in a loop waiting for events to come in. If there are no events, then it will just keep spinning until something comes in. And once the global, when you write a script, right, and we'll see what that means, everything that you write at the global level will happen first, and then the event loop will keep going. So once you're in the event loops loop, it will keep going forever until you close the tab or you shut down your computer or something, right? So this all looks really good at a high level, but it's not magic. It's not magic, right? So we still need some way to count down timers because time happens independent of a program, right? So if this event handler is always spinning, you would imagine if you wanted to count down a timer, you'd have to, every unit, say every nanosecond or every millisecond, every microsecond maybe, you would have to add an event to just count down the timer. This obviously generates a lot of false positive events. So the browser will count down timers for the JavaScript engine. So it doesn't handle that. It also doesn't handle networking, as in it doesn't handle the actual mechanics of sending bytes over the wire, or like receiving the bytes from a socket or things like this. The browser does that. The browser does that. The event loop handles the event that something was sent and the event that something has come back, but it doesn't handle the actual mechanics of sending over the wire. It also doesn't handle the actual pushing to the event queue. So when input comes in from, say, a mouse, it's the browser that does the pushing onto the event queue, not the JavaScript runtime. The JavaScript runtime sees the event queue. It sees that the event queue has grown, but it doesn't physically do the pushing itself. Cool, so I'm going to break out of this. Oops, I'm going to break out of this. There we go. Presentation, and let's go and look at an example. So here I have not VS Code. Here I have WebStorm. And we're going to do a small demo. So let me just increase the font size for you guys. I have a very basic application here. It basically just prints foo, bar, and baz on the screen. And what I want to have happen is I want first foo to be printed as soon as we load the page. But then I want bar to happen next after some time. And then I want baz to happen again after some more time has passed. So let's see how we can use the event loop to do that. Or let's see how we can use functions that we've used before, but with the new knowledge of how the event loop operates to do this. So this is the HTML for that. It's really simple. And here's some code in JavaScript. So I wanted to quickly say a word about this, like the step one of the event loop thing, which is execute your JS script top-down, registering any handlers. That's this. So when JavaScript executes, it does it from the top down. So it will see this function definition and sort of store the fact that there's a function definition. And then it does that for this function as well. And then it does it for this function as well. And then it does it for this function as well. And then it sees this call to foo, and this is at global scope. And you know it's at global scope because there's no indent there, right? When we hit this line, we know that this will be immediately executed, right? So we hit this line, and then foo's called, foo does the thing. This is also a function call, so that gets immediately executed. And all this does is just creates a new text element, sticks it on the, what's it create? H1 element or H3 with some text, and then it just puts it in the body. So this will run to completion. Then we call bar will run to completion, and then we call baz, and then baz will run to completion, right? So this is a very synchronous program. We start down here, and then we go here, wait for the result, then we go here, wait for the result, then we go here, wait for the result. We are going to make this asynchronous. And if you guys have done any events or anything like JavaScript with timers, then you know that there's going to be a function called set timer, or set timeout, sorry, not set timer. And what set timer does is it takes, let's just get rid of this for now. If I look at the documentation, it takes this callback, this handler, and a timeout, which is a number. So naturally, what we're going to do is we're going to have our callback be bar. And let's make this run after 2,500 seconds or milliseconds. So that will be 2.5 seconds. And then we will do the same thing for baz. But for baz, let's be somewhat sneaky. Let's put 0 here. Yeah. So 0 means let's make this happen immediately. Well, that's what you would think. Let's actually put this first. Let's see what happens. What I'm going to do to make this super obvious is I'm going to put a console.log here. Yep, console.log, hello. And then inside of bar and bar, so let's make it baz. Inside of baz, I'm going to put another console.log. And it will say like that. So now if I go back to my web page and I do a Arabic. Okay, well, I won't judge you, Google Chrome, for thinking things. If I just reload this now, you can see this happened really fast, except for bar. It comes here. Hello was printed, and then bye was printed, which is interesting, right? because we would think naively that this timeout, because we're not waiting at all, just don't happen right there. But that's not how it works. So hello was printed first, and then bye was printed, right? So what's actually happening here is this, and this is important to know. Remember, the global scope happens first to completion, always. So we call foo, which calls text inject, which does it's to completion. Set timeout will queue up this event, this handler to execute at least after this many seconds, but it doesn't happen straight away, right? We are still in the process of executing everything that's happening at global scope. So we don't just break out. We have to run everything in global scope to completion first, which is why we set the timeout. It returns immediately, basically, after it's done queuing. And then we console.log. And then we do the same thing for bar, where we queue up after 2.5 seconds for this to run in the event queue. And then that will return. And then we jump off the end of the function. We jump out of global scope. And then at that point, the event loop is going to kick in, look at what events there are, and it will see that there are 2. There's the set timeout one, and for Baz, which can happen right now because we're not waiting at all. And then after 2.5 seconds, it will see that there's the bar event, and then it will go execute the bar event. So this is what's happening, right? We always complete global scope to the end first, and then we will execute the event handlers again for them as well to completion and go from there. So you can see this is important to understand, because sometimes it's rather unintuitive or hard to grasp what's happening here. But for every event handler that we have, it always runs to completion. And then any asynchronous stuff that we do gets pushed onto the end of the event queue. And then we just keep going like that. Yeah, so that's how that works. So if I just get rid of these console, I'll just leave them there, why not? So if I just change this to be 1 second and I go back to my web page and do a reload, then we get foo, and then Baz, and then bar. This one makes more sense, right? Because after a second, we handle Baz's printing, and then after 2.5 seconds, we handle bar's printing. But hello and bye are called in potentially unintuitive, in unintuitive order. So that's that. Let's go back to the presentation. Put me back there. So I'm making an emphasis about the fact that we need that the event loop runs all of its event handlers to completion, because there's a very important thing that you have to understand. The event loop runs on a single CPU, essentially, a single thread is what you'll hear people say, but you can think of it as a single CPU. So what that means is that we have our event handler that gets called. My pointer's gone. There we go. We have the event handler, which is called, and during the period until the handler ends, there's nothing else that can run, not even animations. Nothing will stop an event handler except itself or completing. So what that means is that if your event handler is long running, everything will freeze. Everything will freeze, right? So naturally, the way to avoid this is that if you're doing networking, that is done asynchronously, which is the default, so that's good. But less obvious is that if you're doing a CPU intensive calculation, like, I don't know, multiplying 2 5,000 by 5,000 matrices, I don't know why you would, but you know, you could, that you push this to an environment that's much more apt to doing these intense calculations. And so your best friend, the backend server, is the best place to do CPU intensive calculations. There are other technologies, but we won't be talking about them because they're honestly more of an aside than anything. All right, but I want to show you guys this in practice. So let's go back to Webstone, and we'll close this because we're done. We'll look inside this and this. So again, we'll just increase this. The HTML is not too important. You guys will have all access to this code once we are done. But if we just take a look, see what the app does, it will load this very basic thing. We have a counter, which will start counting when we count. Every second counts up. Then we have our calculator, which we are going to make a very long running calculation, and we're going to see what happens. So let's just refresh this so it stops, and we will go and put in that calculation. So you guys should have covered events already, so I'm not going to explain what all this starter code down here does. Instead, we're going to write a very long calculation. So let's say, I don't know, something is super stupid. Let's do maybe 1 million. 1, 2, 3, 1, 2, 3. And what we're going to do is we are going to count to 1 million with our CPU, because, I mean, that's what CPUs are basically for, right? If you guys don't know what I'm doing, this is a very hacky way of counting. The wrong way. No, that's right. So it's going to start at 100,000. This is actually the post decrement is greater than 0. But if you are super, I don't know, hacky like me, you can just do this. That should be fine. So this will be a quote unquote long calculation. Oh, it's const. I shouldn't do that. I need to make it let. There we go. Let us now go back to here, give it a reload. So did that work? Something happening? I'm stupid. I haven't updated that text. What I want to do is change the text. I suppose I should actually do this properly, shouldn't I? Instead of going backwards. So what I'll do is for let I equals 1. And then whilst I is less than or equal to n, then what we're going to do is increase I. And we will do document dot get element by ID. What did I call the thing? I called it memes. Sadly, it is not memes. I think I called it calc text. That's the one. Text content will be I.toString. Cool. Okay, so this will update the counter now instead of doing nothing. So if we go back to here, give it a reload, and then start calculating, this should count. Well, it didn't do the intermediate values, unfortunately, but it did count up, which is good. Let's now refresh this. And I might add 1 more 0, actually, because that was kind of fast. Let's start counting. 1, 2, 3, 4. Okay, now let's start calculating. Counter stopped. It stopped forever, or has it? There we go. You can see, whilst we were counting to, what's that, 10 million, the counter stopped for like a good 6-7 seconds, right? So you can imagine for animations, right? Or for user input, you can't do anything while this is happening. Like I can't even click. It's just stuck because it's it's calculating. Like the stupid thing that it is. Yeah, it's frozen. And then for really long, yeah, you can see, right? The Chrome even tells me, oh no, this thing is like legit broken because you've blocked the thing. This should be done unless it just suspended the event loop. Yeah, it's just straight up gone. But that you understand, right? You don't want to be doing too much big calculation because you block the event loop. And that's like the antithesis of what we're trying to do here. Cool. Go back to my laser pointer. Right, so this discussion is all about concurrency, right? And how we can do asynchronous or sort of laying the, what would you call, the mechanistic framework for how JavaScript can do asynchronous concurrency. We now know that we have like an event loop, right? And events or tasks can get pushed on the event loop. We register handlers in the form of callbacks or whatever, event listeners. But we still technically don't know what to do about networking, right? Because that's our point, that's our goal. We want to be able to do some networking. And we're going to use this event loop knowledge that we've just gained. And we're going to see the first of 3 approaches of how to do this. So I will see you guys. There you go. Next time, where we talk about XML HTTP request, which is the first of 3 ways to do network request response lifecycle stuff in JavaScript. So I'll see you then.